Dear students, the next chapter is magnetism, and the main content of this chapter is magnetic properties of matter and definition and relation between magnetic vectors B, H, and M, the magnetic susceptibility and permeability, the magnetic properties of diamagnetic, paramagnetic, ferromagnetic, and antiferromagnetic material, the electron theory of magnetism, and the explanation of ferromagnetism. And before going to this chapter, let us make an introduction to the magnetism. The first known magnets were magnetite. Magnetite is a iron core, and the people of ancient Greece and China discovered that this magnetite would always align itself in a longitudinal direction if it is allowed to rotate freely. And this property is used in the design of compass. And this compass was discovered 2000 years back. And this magnetic field of magnetite was mapped with a compass. And from this experiment, it was discovered that the magnet had two magnetic poles, north pole and south pole. In 1600, the William Gilbert discovered that the earth itself is a giant magnet. And later, in 1820, a great physicist, Oersted, discovered that an electric current which is flowing through a wire can deflect a compass needle. That is, an electric effect can be produced by a magnetic field. And thus, the two different branches of physics, electricity and magnetism, which was related, and because of this experiment, because an electric current, it produces a magnetic field. That is, the electricity and the magnetism, which was connected after this discovery of this Oersted. And later, a similar type of discovery was done by Michael Faraday, which discovered that a change in the magnetic field produced a current in a coil of wire. That is, magnetic field can produce an electric effect. The next is a magnetic dipole. We have studied an electric dipole. In the figure, you can see that a positive charge and a negative charge separated by a distance forms an electric dipole. And similarly, a magnetic dipole can be constructed. The magnet are two poles, north pole and south pole, instead of the positive and negative charges separated by a distance in the case of an electric dipole. And this constitutes a magnetic dipole. So every magnet is a magnetic dipole. The simplest example is a bar magnet. When we are saying a magnet, we can say about a magnetic lines. Just as in the case of electric lines, the electric field lines as in the figure, it originates from the positive charges and it ends in the negative charges. Similarly, the magnetic field lines which start from the north pole and it ends on the south pole. Hence, similar to the electric dipole, we can consider a magnetic dipole. Next, the magnetic monopole do not exist. It means that it is impossible to isolate a north or south pole of a magnet. That is, if we divide a magnet into a number of smaller magnets, then each of these smaller magnets will contain a north pole and a south pole. Next is the magnetic field. Just as in the case of an electric field, that is, whenever there is an electric charge, there is an electric field is associated with it. If we are considering an electric charge, then we can say there should be an electric field associated with that electric charge. Similarly, whenever there is a magnet, there should be a magnetic field associated with that magnet. And hence the magnetic field can be defined as a region surrounding a magnet. And if we keep another magnet which is very close to the first magnet, then the second magnet will experience a force. And this region around a magnet is called the magnetic field. That is, magnetic field means it is a region surrounding a magnet, and in that region, if we keep another magnet such so that the second magnet will experience a force, and such a region is called a magnetic field. And here in the figure you can see the magnetic field around a bar magnet. So the magnetic field lines are also represented here, and we can see that the magnetic field is strongest close to the magnetic poles because the field lines are much more near the magnetic poles, and hence the magnetic field is strongest at the magnetic poles, and the magnetic field is weaker as we move from the poles. The magnetic field can be produced by a moving electric charges. A moving electric charge will produce a magnetic field. A stationary charge will produce an electric field, but a moving electric charge will produce a magnetic field. A current loop, it produces a magnetic dipole moment. That is, when a current is passing through a circular loop and it produces a magnetic field, and hence it is equivalent to a magnetic dipole, and it has a north pole and south pole just as in the case of a bar magnet. And next is we are starting with the content of our chapter. The first content is the three magnetic vectors. That is the magnetic induction vector B, and the magnetization vector M, and the magnetic field intensity vector H. First, the magnetic induction or the flux density B. So if we consider a charge which is moving through a point, if it experiences a force, then a magnetic field is said to exist in that point. And that magnetic field can be represented in terms of that force and the velocity of the charge and the charge. That is, a moving charge will produce a magnetic field. If a charge moves, then it produces a magnetic field. And if such a charge is placed in a magnetic field, then it will, because of the presence of this magnetic field, it will experience a force. That is, as in the case of a magnetic field concept, if we keep a magnet near to another magnet, then it will experience a force. Similarly, a charge moving through a point, a moving charge produces a magnetic field, and if it moves means it produces a magnetic field, then it is that point or that charge is under the influence of magnetic field, it experiences a magnetic force, and that force can be represented as F is equal to Q into V cross B. That is, the force can be represented as the cross product of V and B. B is the velocity and B is the field. And the force will be perpendicular to the plane containing the velocity vector and the B vector. And this force is a vector, and here the Q is a scalar, but velocity and B are vectors. And the magnitude of magnetic induction or B can be represented as B is equal to F by QV sine theta, where theta is the angle between the velocity vector and the field vector. And the unit of this magnetic induction is Weber per meter square, or it is Tesla. That is, the field B is equal to the force by Q into V. That is, force is expressed in Newton. Newton divided by the charge Q in Coulomb and the velocity in meter per second. Then Coulomb per second, that is charge by time, it will forms the current. That is Coulomb by second is in amperes. Therefore, Newton by ampere meter. And if we multiply this numerator and denominator with meter, then it becomes Newton meter by ampere meter square. Then Newton meter by ampere is called Weber. Newton meter by ampere is called Weber. Therefore, the unit is Weber per meter square. Or this is equivalent to Tesla. Or 1 Tesla is equal to 1 Newton per ampere meter. Next, the magnetic field vector can be represented as shown in the figure. If we consider the magnetic field lines, then we are considering the tangent at any point on the field lines. It gives the direction of the magnetic field vector B. That is, here the B represented as the tangent at any point on the magnetic field lines. And also the direction of the F and V is given. The B, F and V are mutually perpendicular. That is, F is in a direction perpendicular to both B and V, and the red line shows the velocity component, and the green line shows the field direction, and the field can be represented at any point as the tangent on the field lines. And the number of these lines per unit area normal to their direction is equal to the magnitude of the induction B. Next is the magnetization M. When a magnetic material is placed in a magnetic field, then the material becomes aligned parallel to the field, and the material is said to be magnetized. That is, when the material becomes aligned to the field with respect to the field, then it acquires a magnetic dipole moment. In the figure, we can see the two figures. First one, we show the random alignment of a material. They are randomly aligned. It is in the unmagnetized state. When a magnetic field is applied, then it becomes aligned in a particular direction. That is, it is aligned parallel to the field. That is, the material is magnetized. And this process is called magnetization. The second figure also, we are considering the unmagnetized iron nail. When we are applying a magnetic field, it becomes magnetized. That is the magnetized nail. Or it becomes a magnet. That is, magnetic dipole moment is induced in it. Then the magnetization vector M can be defined as the magnetic dipole moment induced per unit volume of the material. And if V is the volume of the material, then the magnetization vector M is equal to the magnetic dipole moment small m divided by the volume. Thus, the magnetization vector can be defined as the magnetic dipole moment induced per unit volume. That is, the magnetization vector M is equal to the magnetic dipole moment induced small m divided by the volume V. And the unit of the magnetization is ampere per meter. Third vector is the magnetizing field or magnetic field intensity vector H. When a magnetic material is placed in a magnetic field, it becomes magnetized. And the ability of the magnetic field to magnetize a material is expressed by a vector, and it is called the magnetizing field or magnetic field intensity vector. That is, the ability of a magnetic field to magnetize a material is represented by a vector, and it is called the magnetizing field or the magnetic field intensity vector. The magnetic behavior can be studied by keeping the material in a solenoid carrying current. In the figure, we are considering a solenoid with a certain number of turns and a current I is passing through the solenoid. Then this current through the solenoid, it produces a magnetic field within it. And such a field is called the magnetizing field or the magnetic intensity H. The intensity magnetic field intensity vector H is related to the field vector B as B is equal to mu 0 H, where mu 0 is the permeability of free space. The permeability means the ability of a material to pass the magnetic field lines through it. It is called permeability. We are considering the permeability of free space as mu 0, then B is equal to mu 0 H. If we are considering instead of free space a medium having permeability mu, then B will be equal to mu H. And we are considering a long solenoid of n number of turns per unit length carrying a current I, and the magnetic field in the interior of the solenoid is B is equal to mu 0 Ni. Therefore, H can be represented as H is equal to B by mu 0 is equal to Ni. And the unit of H is ampere per meter and the dimension is L raised to minus 1 A. And the magnetic field intensity H is a vector whose direction is same as that of the magnetic induction vector B.